At a recent testing and certification conference, Professor Daniel Sheu from the National Tsing Hua University in Chinese Taipei discusses the ways to improve the performance of manufacturing by identifying unaware failures before testing. Professor Sheu explains the motivation and methods in generating these unaware failures and gives examples of their applications in current industrial development.
My topic is regarding identifying unaware failures, and it's regarding preemptive design for failure prevention. I'll talk about some background and motivation, generation of equipment failure treatment, and something maybe new to you is called subversion analysis, the thinking of and the method of preemptive design. And then it can be applied in the product type application, process type application, and project type application. I explain in this situation how can it be done. I am not a background in terms of testing and certification, so therefore my thought may be a little bit different from people in this field, and I think that may be stimulating for some of you. We know that testing is important, but from industrial engineering viewpoint, testing makes no added value. Why? Because it does not add function to it, it does not change parameter to it, right? So the ideal testing is no testing. If we can achieve that situation, that would be best, right? We don't need to spend time for testing. Of course, there are realities you need to carry out, but that I think should be as a goal. So minimize testing, where a product works by design and manufacturing, is actually better than by testing itself. And the ideal goal is no need to test at the manufacturing. We get all the tests needed, and we've done it in the design and in the manufacturing. That's the situation. Now, regarding the testing, I know that the major purpose for that is to assure the reliability, and it works, right? FMEA has been very helpful in helping engineers identifying potential failures and design procedures to prevent failure of any hardware and software. And everybody uses that a lot, therefore. However, FMEA can only work with the known failure, because some failure has been happened before. Therefore, I know it. For the next product, I introduce FMEA to design it out. The problem, actually, the most difficult situation is the failure that we are not known. Like you are fighting with your enemy, you don't know where your enemy is. That is the most difficult situation to do, right? So to talk today is regarding how can we identify unaware failure. The failure has never been before. How can we identify that? And because that is much more difficult than dealing with the known failure. Okay, that's my topic. If we know what failure it is, we can always design some way of preventing and handling it. And now here, I propose a systematic way to identify potential unaware failure and prioritize them, so people can design in some mechanism to design the failure out before they may occur. And this is based on systematic innovation method, or from the trees itself, the expansion on that. And now talk about failure preemption. If you look at the generations of equipment failure treatment, the first generation is replace after failure. The machine fails, then we replace it, we fix it. And that's the after fact, too late, right? And then nowadays, people have been using preemptive maintenance. Okay, so how many disks has been used, how long has the system used, and then we do the preventive maintenance on that. The problem is that you may over-maintain it, or you may under-maintain it, such that the failure happens, okay? And now, the state of the art today is regarding prognostic maintenance. It's actually the predictive maintenance, and this is the state of the art technology. But the problem is we still need to take down. The way to do that is that we measure all the vital signs of the system. And when the system data comes close to certain kind of failure, maybe 80% approaching certain kind of failure, then we stop the system and replace the parts that may cause failure. And in this way, we don't need to encounter failure. And that's the prognostic maintenance right now. The one that I'm proposing today is what I call failure preemption. Okay, I call it preemptive redesign. Okay, there are two ways. One is preemptive redesign. We identify failure and redesign the system. The other one is the design into design out. That means that if I can identify a certain kind of failure, which has not been happened before, but I saw this may be one of the failure mode that may occur, right? If I can identify the unaware failure, then I know the mechanism of producing this failure. Then I can design in certain kind of mechanism to design out the potential failure. And that's the key thing today on this situation. Okay? This is related to the history of quality sources. At the beginning, what people do is quality through testing and inspection. Right? So when it comes out, right, this is bad, so take it away, and this is good, let's go. And that's quality through testing and inspection. And then quality through preventive maintenance. Okay, that's what I've just mentioned. We do the preventive maintenance, we do the preventive way. Okay, and then the quality through monitoring, which is the predictive failure prevention, and in the manufacturing. Okay, that is much better than the previous two generations. Now, the fourth one that I'm proposing is quality through design. Okay, we either redesign the system after failure, that's aware of failure or known failure, or we can understand what may be the failure, even though it's not happened before, but we can identify the unaware failure and then design a mechanism to design out potential failure. Okay, that's the thing that I'm proposing here. Now, this is regarding a concept called subversion analysis. Subversion analysis is a special trees way of thinking. Trees is a theory of inventive problem solving. Okay, I don't have time to go through this thing, but you know that something called trees there. It's part of systematic innovation. Okay, so the way of subversion analysis thinking is like this. Many people are trying to do, if this fails, and understand what the reason of this fail, and then we can prevent it in the future. Now, subversion analysis works the other way around. That means the system is good. Right now it's good. But I think about how can we break the system? So we try to identify some ways of breaking the system. As long as I can find some way of breaking the system, I can understand the mechanism behind it. Therefore, I can design in certain kind of mechanism to design out the future failure. That's the idea on that. So instead of fixing it or preventing it, we do how can we break the system? And from this, we understand the mechanism of it, and we can prevent it. Okay, so we can use subversion analysis, and the other one is we can use thought-provoking question. We ask ourselves some key questions which can stimulate our thought regarding how can we identify the failure. The subversion analysis can be used in several ways. Usually, we classify failure in terms of two types. Type 1 is regarding the known failure. It happened before, we have seen that before. Type 2 is regarding unknown failure mode, which I said unaware of failure, because it never happened before. How do you know it may happen this way? And that is the most difficult thing. Okay, I'm focusing on this type 2 here. And the key is failure identification and avoidance for unaware failures. And that can be for devices, which is a physical system, or for processes. The method for failure preemptive design, there are three major types of preventive design. Actually, the application, there are three categories of them. First is device type application. What I call device type is, this is a physical system, an actual product or actual machine, a physical system. And then we try to define some way of failure preemption on this physical system. For this, we can use function component decomposition of the system and consider potential failure mode of each function and component. And this is part of trees thinking method. I'll elaborate a little bit more later. The second type is process type application. The way to do that is based on decomposition of process flow charts and consider potential failure modes of each process steps and in-between steps. The third type is project type application. It's based on work breakdown structure. Many of you know about project management, right? If you know about that, the project management can be decomposed into many, many tasks, right? And then decompose it further. And this is called work breakdown structure. We can use the work breakdown structure to identify potential failure of each task. All this can use trees, subversion analysis, and thought-provoking question, TPQ, to stimulate potential failure more. And once we can answer the questions, right? And the answer will indicate us what kind of failure it may be. And that's the way to identify potential unaware failure mode. I'll give you an example regarding how to identify potential failure for physical systems, the first type of it. Device failure mode, okay. Any physical system can be presented in trees functional analysis form. The system is very complex. It's a physical system, very complex. The way to do that is that we break down, and people know that 1,000 years ago, when we encounter a very difficult question, first we break down the system into subsystems, and then look at what may be the situation in the system, also the situation in between systems, between systems. Therefore, we can use the functional relationship between components. For example, this device, or this equipment, or this physical system, we can express it in terms of the diagram on the right side. This is called a functional diagram. Functional diagram. It composed of two aspects. First is it identifies all the components, all the subcomponents. Each one can be further divided into smaller components, but it identifies the subsystems of the big system and identify the relationships between all the subsystems. And that's the function and the component, function and component. And then we look at potential failure from the functions, from those functions. How can we break this function? What kind of function it may produce, and so on like that. And also we look at the failures on those components. Okay, so in this way, we look at every fundamental aspects of the system's function. We take function as a handle, take it out, and with this function, this is component 1, produce this function on component 2. The one producing function, we call it tool. The one receiving function, we call it object. And look at the function, what kind of failure it may be. There are only countable ways of functional performance. First is normal situation, no need to worry about the failure. The second is a harmful function. This component may produce certain kind of harmful function, and harmful function is a failure mode, right? For harmful function, we ask, what harmful function can this C1 component produce? The other way is, how can we make harmful function by C1? We try to make the system fail. We try to make the function harmful, right? So how can we produce a harmful function by C1? If the function is excessive, or we can look at what useful function can become excessive. The function is good, but too much, that's not good, right? So think about what excessive function this may produce, right? And consider all the useful function of the tool. And then we can also ask, how can we make the useful function excessive? If we are able to make any useful function excessive, that means we identify certain kind of failure mode. And we can work on that from there. Now, the other thing is the insufficient function. What useful function can become insufficient? How can we make the useful function insufficient? And the next one is effective. What effective function can this component produce? How can we make a function ineffective? And the last one is missing function. We need a function, but the function is not there. That's called missing function, right? And we look at what are the missing function? What can be missing function there? Okay, or how can we make the function missing, an existing one missing? So these are only countable categories of functions. That is no good, or good, right? So we look at these directions, somehow pretty much comprehensively look at all classes of situation. And on each class of situation, we say, how can this produce failures? okay, and what kind of failure this situation can be produced. Then we can identify a list of the failure modes there, and we start from there to understand the mechanism of each failure, and then design in mechanism to design out those future failure, even though it's unaware of. Okay, so all the above thought-provoking questions may stimulate failure modes systematically and nearly comprehensively. Of course, the failure may be very, very, very many, right? So some sort of screening method, preliminary evaluation method can be used to prioritize the failure modes or screen out highly unlikely ones when the number of the identified failure is too many. Okay, that's the situation. Now, regarding the component failure, most component failure produce corresponding functional failure, except cosmetic failure or reliability issues there. Therefore, most component failure can further be identified from already identified functional failure of that component. But in addition to the functional failure, for each component, we can ask, how can we make the component fail? Then from there, if we find the answer to this, we identify the failure mode regarding that component. Also, if the component is big, right, we can further divide the component into its subcomponents and use the same way to identify the functions between subcomponents. So here is the structural component failure mode searching, missing components. I need a component here, but it's missing, right? And then we say, how can we make the component missing? If there's some way the component may be missing, right? Now the other one is an improper component. The component itself is not the right one, or the material is no good. How can this become wrong, or the structure become wrong? And then for each component, right, there are always input signal or input things to it and output things from there. We can ask what kind of improper input can be fed into the component? What kind of improper output can be out of the component? In what situation we can produce this kind of errors, failures? With that, right, we can also pretty much comprehensively think of all the categories of the failures with respect to this component. Okay, that's how it works here. And that's the first type, which is regarding physical components. Now, regarding process type of application, any process type application has flowchart or process chart. Most commonly used flowchart symbols, the hour, like this, right, stands for beginning or an end. The rectangles are steps in the flowchart process itself. The arrows signify the flow direction. The diamond signifies the decision point, right? And then there's a storage or output. Only this kind of 5 categories of the flowchart components. And for each category of flowchart component, we can think about what are the failure situations for each category. So for each process step or element, we ask, how can we make the step fail? Or how can the step be missing? Or for each directional flow, we ask, how can the connection fail? Or how can the connection missing? Okay, how can we make the connection missing or fail? On this, we can identify the corresponding way of making the element fail. Alternatively, we can use flow process chart to analyze the failure modes in the manufacturing situation. That's particularly in manufacturing situation, it's very helpful. I'll give you an example regarding this manufacturing process. This is from actually Procter & Gamble's situation. They are making a soap. The first is making liquid soap. Second is process liquid soap by pipe coming out. The third is fill liquid soap into the mold and then solidifying the soap in the mold, 8 hours, long time. Then remove the soap from the mold and then polishing it into the shape we require, and then we wrap it, become the soap that we sell. For this situation, right, we can draw the process flow chart for this manufacturing process. Okay, for example, you can see 7 stations to produce this thing. These are the corresponding symbols for the station steps that for each one, it actually has the processor, the functional operation itself, and the object. Here the object is the soap itself that we are making. So actually, at each station, it only have limited types of elements. For example, we have processor, we have operation function, we have the object, right? And then you divide the processor into physical elements to find out what are the situations. We can use the previous way of dividing the system into component and function, something like that, to identify the component or elemental failure mode. So for each processor, we ask thought-provoking question. How can the processor fail? How can we break the processor? And further break down the components for each processor, because there may be many components. Okay, and then for each operation or function, we ask, how can the operation or function fail? How can we make the operation or function fail? Okay, for each object, we ask, how can the object fail? How can we make the object fail? And think of some way to make it fail. So in this way, you will be able to identify many types of failure situation. And each of them can give you the hint regarding the failure mode. That's regarding the manufacturing process. The third type that I'm going to share with you is identifying failure modes for projects. We all do a lot of projects there, right? A project can be broken down by its work breakdown structure. Okay, for example, like this one, work breakdown structure is a deliverable-oriented hierarchical decomposition of the work to be executed. That's said by the project management book of knowledge. For example, here, right, we building a deck, right, consists of site preparation, purchase material, construct deck, clean up, and each one can be broken down into details. Now, each one like that can bring it down into details. And then at the end, when you break it down, it becomes tasks. There are many tasks to form the whole task, the whole project, right? So each one can eventually break down into tasks. And we look at each task. Each element of the work breakdown can further be divided into tasks, right? That's called work package. And the key elements for each task only have these kind of things. First, what are the deliverables? What is the performance specification? The other one is the schedule. What is my schedule duration of start and end to produce this result? And then is the actual duration. When does the work actually started and when does it actually done? And then budget and cost. And then for each component, for each task, it has performance measure. What kind of reliability, what kind of functionality it has to achieve, right? And then who is going to do the work, responsibility. And then precedence relationship between the tasks. What tasks before precedes this task? What tasks after this task, and so on. So for each element, there are only countable ways of featuring them, right? So we look at each one, we think, well, how can I make the deliverable fail, right? And then how can I make the schedule work, or make the schedule fail, or delayed, right there? And how can I make the cost overrun, something like that, right? And then who is going to do that? How can I make the person fail to perform this job, right? And this kind of thing, okay. And then, so actually we can ask, what can cause us to meet the task element? Each one is a task element. For each task, we examine its fundamental essence of the task and find out what are the things that may cause this fundamental element to fail. And anything that can cause any of the fundamental element to fail could be the failure mode. And many of them probably is unaware of. That's the situation like that, okay? And after that, I suggest 3 types of ways to identify unaware failure mode, right? One is physical element. A physical element, we use function analysis, okay, to look at the component and the functional relationship. The other one is the process. We can look at flowchart or process flowchart in the manufacturing situation. The third one is project. We look at the work done structure, right? And then going down to the tasks and to look at the fundamental element of the tasks and say, how can we make the element fail? Or what kind of fail this element can have? And with this, right, we accumulate a lot of failure modes. Of course, some of them may be, this element is very, very robust. Therefore, you can say this is very unlikely. So with that, we can use the regular FMEA to prioritize failures. In this way, we pretty much can comprehensively thought of all the failure situations. Okay, and then we use the FMEA to prioritize them. Some of them may be not important, and then we can drop out. And many of them will probably be important, and we will keep it there. So in this situation, we can identify a lot of failure. I'll give you some summary and conclusion. First, testing is to assure quality and reliability of products. From the industrial engineering viewpoint, testing is not value add. Sorry to say that, but that's the fact, I think. But of course, because the technology is not yet there, therefore we still need testing and certification, this kind of thing. But the goal must be, how can we minimize or nullify testing need? So the best testing is no testing, or at least minimize testing. And this may be achieved by failure preemptive design and high-performance manufacturing. That's what I'm proposing. And second one is FMEA only identify failures that happened before. This kind of failure, because it happened before, and you understand it, therefore it's easy to handle. The most difficult problem to handle is something that you are unknown. You are unaware of its existence. It may occur. And even you are not know what's going on, and it fails. That's the most difficult thing, and we are addressing this. Okay, and this is the situation. Then generational equipment failure treatment, including replace after failure, the first generation, preventive maintenance, second generation, prognostic maintenance, also predictive maintenance, and then failure preemption method. And the way I'm proposing is regarding how to do failure preemption. The first stage, identify unaware failure. It is possible to design a mechanism to design our future failures, including unaware failure, with the method. Okay, and we propose the 3 types of failure identification method for physical situation. First one is physical situation, the actual device itself, equipment and so on, actual product. Second one is process operation. When we're doing some process, right, we can use the process type method to identify them. The third one is project type application, using systematic decomposition of functional model, process flow model, or work breakdown structure. And then use thought-provoking question with subversion analysis method to identify them. Okay, so actually the idea is simple. The system is so complex, so difficult, I don't understand it. Well, break down into components and the relationship among the components. And you look at the relationship, how can we make this fail? We look at a component, how can we make this fail? Okay, that's the general way of thinking regarding physical device, regarding process, regarding project, all the same idea. Okay, and then you try to generate failure upon these elements, and that's the most important thing. Thank you.